All right, everybody. Today we're going to be covering the third topic in this AP chapter, which is going to be dealing with position, velocity, and acceleration. So a lot of this is going to be familiar because we've worked pretty extensively with these functions in the past. A lot of the new stuff is just going to be relating it to what we've done with our rate functions and net change. So when we started initially working with position, velocity, and acceleration, we knew that to go from position to velocity, we would differentiate. And similarly, to go from velocity to acceleration, we would also differentiate. But now that we've learned how to integrate, we can go backwards as well. So if I have acceleration and I want velocity, I can integrate to get information about velocity, and same going from velocity to position. I can integrate. So we can work backwards now that we have the ability to integrate. And so the only thing I'm going to add to this diagram is just in terms of notation, position we commonly reference as our S of t, velocity is v of t, and acceleration is a of t. So what we're going to do is kind of review some of the vocabulary we've used in the past around position, velocity, and acceleration, and introduce a few new ideas. And again, tying this into what we know about rate functions and net change. So to start off with, if I'm talking about the new position of an object, what I'm really talking about is the location of the object at a specific time. Now, there's a few ways we can get this information. Obviously, if I have a position function, so if I'm given S of t, to get the location of that object at a time, I can just calculate S of t. Now, as we go through this chapter, or through this section, it's not always going to be that easy. We're not just going to be given the position function. A lot of times we'll be given the velocity function and asked to find the new position. So now what we're really going to have to consider, if I want the position at a time t, I'm going to have to consider the initial position plus the net change. So in other words, where did it start, and then how much further did it go? So for us, the initial position is just going to be S of 0, or some initial position that the problem gives us. And then the net change we're going to get by integrating our rate function, which in this case is velocity. Okay, so next, for the total distance traveled, right? This describes the total distance the object travels between two specific times, right? And this is going to work just the same way as when we were talking about total area versus calculating the integral, which gave us the net area, which actually took the positive areas and then subtracted the negative areas. Okay, so for option number 1, we said when we were doing areas, if we had a calculator, we could just integrate the absolute value. And that's going to be the same thing here. If I want the total distance traveled between two times, I'm just going to call them T1 and T2, we could just integrate the absolute value of velocity. So if we're given a function and we can use a calculator, we would just integrate the absolute value. Now, if we don't have our calculator, just like when we were doing area, we have to take our velocity function, set our function, set it equal to 0, and then we're going to split it up into two integrals, or however many, split up the integrals based on the zeros, and then add their absolute values. And again, as we go through, we'll be doing specific examples of each of these. Okay, displacement now. When we're talking about displacement, all we're talking about is how far away is the object from where it started. So we're not concerned with, well, how far in total has it traveled? We just want to know how far it is from where it started. And what I want us to really realize here is the displacement is the net change. Right? So when we were talking about this net change up here, we were talking about displacement. So for option number 1, obviously if I had a position function, I could just subtract my new position from my starting position, and that would tell me how far I am from where I started. However, like I mentioned, a lot of times in these problems, we're not going to be given the position function. We're going to be given the rate function. Well, I know net change is just the integral of my rate. And in this case, my rate is v of t. So I'm going to integrate my velocity function to get the net change or displacement. Okay, last part is speeding up versus slowing down. So just like we did before, to figure out if we're speeding up or slowing down, we're going to compare the velocity and the acceleration. Okay, we know we're speeding up when v of t and a of t have the same sign. And then we're slowing down when they have different signs. Okay, so that just kind of gives you a preview of the vocabulary you're going to hear as we go through these problems. So let's look at some problems. All right, so number 1, nice easy example, but it's going to illustrate really nicely the difference between the idea of the total distance traveled versus displacement. Okay, so we have an ant who's traveling by taking 2 steps forward and then 1 step backward over a 2-second time interval. So if you think of our little ant, he's going to go 2 steps forward and then he comes back 1 step backwards. So the total distance traveled over that time interval, I just want to know how far in total did he walk. So he walked 2 steps plus 1 step, so his total distance traveled is 3 steps. Now, on the other hand, if I want to know the displacement, right, what I'm asking is, how far is the ant from where he started? And so if I think of it that way, if he started here, went 2 and came back 1, he's only 1 step from where he started. And that's the displacement. Just how far did he actually get over that time interval? So again, it's going to be really important that we're clear on the difference between displacement and total distance traveled. Okay, number 2 says, suppose the velocity of a particle moving along the x-axis is given by our function v of t for t between 0 and 2. Okay, this problem should look very familiar. You've done problems like this before. So if I want to know when the particle is moving to the left or to the right and when it stopped, I know I need to first figure out where v of t is equal to 0. And then we'll do a sign analysis to figure out where is it positive and where is it negative, and that'll help us determine right, left. Okay, so let's go ahead and take a look here. So my function was 6t squared minus 18t plus 12. And so my first step, I'm going to make this much easier to work with by factoring out that 6. And then I've got, let's see, t minus 1 and t minus 2. So it's nice and easy to factor. So I know it's equal to 0 at time equals 1 and 2. So now I'm going to make my table. I'm looking at v of t. Let's see, it's from 0. I've got points at 1 and 2. And now I'm just going to check the sign by testing values in each of these intervals. So let's take 1/2. I'm going to go back to the factored form here because it's much easier to check. If I have 1/2, this first factor will be negative. My second factor is going to be negative, so I know I'm positive between 0 and 1. If I pick 1.5, now my first factor is positive, my second factor is negative, so I'm going to be negative over that interval. So now I'm moving to the right where velocity is positive. And again, since this is first derivative, we're going to use a closed interval. So I'm right from 0 to 1. I'm left from 1 to 2. And then I know I'm going to be stopped at t equals 1 and 2. Now, if there were units here in my problem, I would absolutely include them, but here we haven't been given any units. Okay, now in part B, here's this word displacement. Right? And so again, now I'm thinking, okay, where is this particle? How far is it from where it started? Well, we said displacement is just the net change. And the net change, we know we get by integrating our rate function. And in this case, our rate is velocity. So I want to find the displacement for the given time interval, which was from 0 to 2. So all I'm going to do is find the integral from 0 to 2 of v of t dt. So the integral from 0 to 2, my function was 6t squared minus 18t plus 12. Now, one note when we're writing our integrals, please do not forget your dt or dx or whatever it may be at the end. You can kind of think of this symbol, the integral symbol, and the dt kind of as parentheses that open and close that integral. So you need to make sure your notation is really good, especially for the AP exam. You need to have these integrals set up correctly. All right, now is the easy part. All we have here is a definite integral that we're going to evaluate by anti-differentiating. So my antiderivative of 6t squared is going to be 2t cubed. Let's see, minus 9t squared plus 12t. And I'm integrating from 0 to 2. So let's see, 2 cubed is 8 times 2 is 16. Minus 4 times 9 minus 36 plus 24. And if I evaluate at the lower limit, obviously those all have t's, so that's just going to be 0. So now I have negative 20 plus 24. My displacement is 4. Okay, now I want the total distance traveled by setting up one integral and using our calculator. So if I can use my calculator, I'm just going to integrate from 0 to 2, because that's my time interval. And I'm going to integrate the absolute value of my velocity function. So let's go to the calculator here, if I can find mine. Here we go. And do this. Okay, so we're going to use our Math 9. And we're going to go from 0 to 2. Now I'm going to go to Math, get my absolute value. And I'm going to type in my velocity function, 6x squared minus 18x plus 12. And then I'm integrating with respect to x. And we're going to get a total distance traveled of 6. Okay, so now we're going to do the same thing, but we're going to do it without a calculator. So we said our first step was to find where our velocity is equal to 0. Well, we already did that up here, so I'm going to just grab these values. I know that happens at 1 and 2. And so now I need to split up my integral. I'm going to integrate from 0 to 1. And I need to find from 1 to 2. So my antiderivative is 2t cubed minus 9t squared plus 12t, and I'm going from 0 to 1. So here I'm going to get 2 minus 9 plus 12. So let's see, negative 7 plus 12 is going to give me 5. And down here, same antiderivative, but I'm going from 1 to 2. So I'm going to get, let's see, 16 minus 36 plus 24. And then minus, well, let's see, we just evaluated at 1, and we said that was 5. So we're subtracting 5. So now I have negative 20 plus 24. So I have 4 minus 5. It's going to give me a negative 1. So now I've got the values of those integrals, and we're just going to add their absolute values. So my total distance traveled is going to be 5 plus the absolute value of negative 1, which is going to give us 6, which matches our calculator answer. Okay, so now we've done some problems where we're working with a velocity function. In the next problem, we're going to look at the same types of ideas, but we're given a graph for velocity instead of the actual function. So here, the graph given shows the velocity function for an object moving along a straight line from t equals 0 to t equals 8. And it's telling us now at t equals 0, the position of the object is 5. So here we're being given an initial position. All right, so part A, when is the object at rest? I know that happens when velocity is equal to 0. So I'm just going to look on my graph and find, well, when is it equal to 0? And that happens at t equals 5 and 8. Okay, next part, evaluate the integral from 1 to 6 of v of t dt, and then explain the meaning of that result. So let's look at this. Since I have a graph, I know to calculate that integral, I'm going to be doing the area between the curve and the x-axis. So if I start at 1, it looks like I can get a trapezoid from 1 to 3. So let's see, the height of that is 2. One of the bases is 1, and my second base is 2. Then I'm going to add the area of this triangle, so plus 1/2 times 2, height of that is also 2. And then I have to subtract this triangle here that's below the x-axis. So minus 1/2, the base is 1, and the height is 2. So let's see, we have 3 plus 2 minus 1, or 4. Okay, so the value of our integral is equal to 4. Now, we have to think about what that means. So, we integrated our rate function. Velocity is our rate function. We know that if we integrate rate, we get the net change. And we know in this context, hopefully by now, it's starting to click that net change in this context is the displacement. Okay, so the meaning of it means the displacement of the object over the time interval let's see, what were we doing? T equals 1 to t equals 6 is 4 units. Or in other words, really what we're saying is the object is 4 units from where it started. Okay, but the key there is this word displacement. Do you know that integrating velocity gives you displacement? All right, so now we're asked a slightly different question. Right, now we want to know what is the position of the object at t equals 5. So if I want to know its new position, what this is really asking me is where is it? So I know I need to consider, if I want to know where my object is, I need to consider the initial position plus the displacement. So where did it start and how far did it get from where it started? Well, thinking through this, I know displacement is net change. And I know to get net change, I'm going to integrate velocity. So let's see what we know. My initial position, they told us that at t equals 0, the position of the object is 5. So I know that my position is equal to my initial position, 5, plus the integral from 0 to 5 of v of t dt. My initial position plus the net change. And again, we're being careful here. They gave us the initial position at time equals 0, and so that's why I need to make sure my lower limit of integration is also 0. Well, we calculated this, so let's see, it's 5 plus. I know when I did from 1 to 6, the only thing I need to take off is this minus 1. So that is just going to have a value of 5. Again, using areas. And so then, let's scratch that, because actually now we're integrating from 0 and we were not above. So let's see, the integral here, I have to consider this piece of the area as well. So from 0 to 1 is 1. Then I know from 1 to 5 is 5. All right, so my new position then is going to be 5 plus 6, or 11. So 11 gives me the position at time 5. Okay, now for the total distance traveled over 0 to 8. I know from 0 to 5, I can just take the integral of that, or I can take the area under the curve, because that's positive. Now, the only thing I have to be careful of is, since I want the total distance traveled, I can find the area between the x-axis and the curve from 5 to 8, but I just need to make sure to take the absolute value of that area. So I'm going to find the area from 0 to 8, and again, that's going to be the integral from 0 to 5 of v of t dt plus the absolute value of the integral from 5 to 8, v of t dt. Okay, well, we know the integral from 0 to 5 is 6, plus we're going to add the absolute value. Let's see, we have a trapezoid here with height 2. Its base here, what would that be? It looks like 1 plus 3. So that's going to give us 6 plus, I'm sorry, and that would have been negative because it was below. So 6 plus the absolute value of negative 4, which is just going to be 6 plus 4, or 10, is the total distance traveled. Okay, then the last part for this question, at time t equals 2, is the object speeding up or slowing down? So explain our answer. So the first part we need to do, we know we need to compare velocity at time 2 and acceleration at time 2. So velocity of 2 is easy. I can just get that from the graph. And it looks like it's going to be about 1.5. The actual value isn't as important so much as I know that's going to be positive. Now, for acceleration at 2, well, I know that's the derivative of velocity. Right? So really what I'm comparing here is the slope of velocity at t equals 2. V prime of 2 is just the slope at that time. So if I look to my graph, I can see at time 2 I have a positive slope, so velocity is going to be greater than 0 as well. So we would say at t equals 2, the object is speeding up because v of 2 and a of 2 are greater than 0. Okay, there's still a couple problems left, but because this video has gone so long already, we'll save those for class tomorrow. We can work through those quickly at the beginning of class, and then you'll be on to your practice.